Hello, so my name is CHAUDHRY and today I am presenting my microprocessor lab project for PHC 306 course, a keypad controlled decimal timer which is built on the 8085 LCD training kit. So this project interfaces two peripheral modules through the 8255 programmable peripheral interface, which is a matrix keypad and the kit's built-in LCD display. And this implements a real-time decimal counter controlled entirely in the 8085 assembly language. So everything that you'll see here, the scanning logic, the decimal conversion, the display output, everything is implemented in machine code, which is entered byte by byte into the RAM of the 8085. So before starting the actual presentation, let me just start with an outline of what I'm going to present. So I will start with the background and the objectives, and then I'll go through all of the hardware architecture, what is connected to what and why. From there, I'll go into the technical details, how the 8255 PPI is configured, how the matrix keypad scanning works, and how the LCD controller protocol works. And then I'll walk through the actual program, the memory layout, the flowchart, and the code itself, including the decimal conversion algorithm and subroutines. After that, I will cover the debugging challenges that I hit during implementation. There were several interesting ones, and after that, I will finish with the demo, the results, the applications, and the conclusions. Okay, so let's begin. So let's start with the background and objectives. The 8085, as I'm sure you know, is an 8-bit microprocessor which was introduced by Intel, and it's been the standard teaching platform for microprocessor architecture for quite a long time because it is quite simple and you can trace every hardware interaction. When you write a byte to a port on the 8085, you can see exactly what signal changes on which pin, and there is no abstraction hiding or under what's happening. So that is what makes it valuable for learning. My specific project had five specific objectives. First was to interface the matrix keypad through the 82552 port using software matrix scanning to detect individual key presses. The second was to display a real-time decimal counter on the kit's built-in LCD display, which updated every second. The third was to implement user control, that if you hold the key 1 on the keypad, it resets the counter to 0. The fourth was attempting to use the LCD module as a secondary display showing a static label. And finally, the fifth was to write the entire program as assembled machine code so that it wasn't too long. It wouldn't take too long to write because you would also need time to debug that. So I achieved four of the five. The LCD module that I tried to also make work and have a static display didn't work, but that wasn't the main part of the project anyways. Okay, so let me describe the hardware architecture to you guys. The central unit is obviously the 8085 training kit. It contains the 8085 CPU and it has an LCD display that is built into the kit. It has a ROM and it has two 8255 PPI chips which are accessible through 26 pin connectors which are labeled J1 and J2. The ET KB keyboard module was a 20 key matrix keypad, which is basically you have five keys in four different rows, and the keys are connected in matrix. The columns connected to the port A of the second 8255, which was configured as the input, and the rows were connected to port C, which was configured as the output. The LCD module is a 16 by 2 character LCD, which is driven by a controller, and it has a database that connects it to the port A of the first 8255, and it has control signals for read write, and it was connected to the port C. So both modules connect to the main microprocessor kit via 26 pin FRC cables. Uh, this becomes relevant during our debugging, which I will discuss in detail more later. Now let's take a look at the diagram for how all the components interact. So the 8085 kit is in the middle. To the left is the 82551 port, which is also called the J1 port, and to the right is the J2 port, the 82552 port. The 8255 has its port A on address 00H and its port C on address 02H. For the 8255, it has its port A on address 08H and port C on address 0AH. So the port C carries three control signals that tell the LCD whether it's receiving a command or data, and that triggers the enable pulse. The kit's built-in LCD, it doesn't go through either 8255. It is controlled directly through the monitor ROM subroutine calls. As you can see in the diagram, the kit LCD, it is not connected to either of these. It is connected directly to the CPU. So we have two completely independent display paths and two 8255s, which is one dedicated to each peripheral. Let's take a second to really understand the 8255 because everything in the project really depends on it. The 8255A provides 24 input-output lines, which are organized as three 8-bit ports, port A, port B, and port C. A single byte written to the control word register configures all of them simultaneously. Look at the control word format on the screen. Bit 7 must be 1 to indicate that this is a mode set operation. Bits 6 and 5 select the mode group for group A. We use mode 0, which is simple basic input output because that's all we need. Bit 4 sets the direction of the port for port A and so on for the other ports. For the 82551, which drives in this case the LCD module, we want all the ports as output. So we write 80H, that's such that bit 7 is 1 and everything else is 0. So that means that all the ports are in outputting in mode 0. For the 82552 part, which interfaces with the keypad, we want port A and port C as the output, port A as the input. So we write 90H in the code, and the only difference is the bit number 4, which is now 1, which makes the port A as an input. These two initializations, out to 80H and out to 90H, these are the very first instructions that a program executes. So now let's look at how the matrix keypad works. So the matrix keypad basically solves a wiring problem that if you have 20 keys and you dedicate one wire per key, you would need 20 input-output lines. But if you organize keys at intersections of rows and columns, you only need 8 columns plus 3 rows, which is 11 wires for 20 keys. The scanning algorithm works like this. You drive all the row lines high simultaneously and you write uh, data to the port C, which means that then you read from the port A. And if no key at all is pressed, then all of the outputs, all of the columns are pulled low. But if a key is pressed, it would short one row line to one column line, and then we would read a non-zero value. The bit position of the non-zero bit tells you which column the key is in. For our project, we only needed the key number 1 specifically. Key 1 is in column 1. So basically, when the key 1 is held, the port A reads 02H in hexadecimal. So we compare the port A value against that 02H. If they match, we jump to the reset block, and if they don't, we continue and we keep polling every 100 milliseconds. So this is basically the entire keypad interface. If we look at the LCD interfacing theory, it accepts 8-bit parallel data, and every write, whether you are sending a command or a character, it basically follows the same sequence. You put the data byte on port A, and then you send control signals on port C. And if we send signals, like for example, RS is bit 0 and read write is bit 1. So in this case, 0 means write, which we always do, and E is bit 2, the enable signal. The controller latches data onto the falling edge of E. So the sequence is basically that data on port A, we set RS and the read write appropriately, and then we bring E high, and then after waiting briefly, we bring E low. So the controller reads data from that falling edge. So for a command, basically port C is 04 in a hexadecimal, and for a character, port C is 05. So before the LCD will display anything, it needs an initialization sequence. It requires specific commands set in order on power up. We set this function three times, that is the command 38 in hexadecimal, and it reliably establishes the 8-bit interface mode. Then for display, we set 0C in hexadecimal with the cursor off, and then 01H to clear the display. Finally, we set 06H to set the entry mode, which means that our cursor will advance right after writing each character. If we look at the DD-RAM and the character addressing, basically the display has 80 bytes of display data, a RAM, DD-RAM, and each byte holds the ASCII code of one character on screen. So for a 20 by 2 display, row 1 occupies DD-RAM addresses 80 to 93H, and row 2 occupies C0 to D3H. To position the cursor before writing, we need to set a DD-RAM address command. This is simply the DD-RAM address that you want with the bit 7 forced to 1. And with this, we can set the display each character at a time as we want. After we position the cursor, every character write advances it automatically. So if we want to write, let's say, the word timer at position 0 of row 1, we can set 80H as a command to set the address, and then we can write the ASCII codes for the each individual letters one after the other. And after every time, we will call the WR character command, and the cursor it advances automatically with each write. This is exactly what a startup block does. It sets the cursor and then writes each character of the label. Now, let's look at the memory layout for our program. So, the LCD manual specifies that the WRCMD subroutine, it must be at address 2048H, and the WRCHAR routine must be at address 2056H. The manual's examples also calls those addresses. So this forces a specific layout. We have to start at 2000H, and we place a jump instruction that jumps over the subroutine to the address where the startup block lives. The subroutine set at their fixed addresses 2048 to 2071. The timer loop it runs from 2080 to 20CDH, and the startup block, the LCD initialization, and the label writing code. That runs from 20D0 to 213C. The counter storage is at 2500, which is basically a single byte in RAM, which makes the counter data persistent. Otherwise, it would kind of keep starting at the same number, but this makes sure that it keeps on advancing one after the other. The total program size for this program was approximately 200 bytes, and as you can see, it was spread around the memory like this. Here is the broad flow of the program. The execution starts at 2000 and it hits the jump command and then it goes to 20D0, the startup block. The startup block initializes the 82551 for output. It initializes the 82552 for keypad and sends the six LCD initialization commands to the LCD module which is built in the microprocessor kit. It writes timer to line 1, it writes reset to 2, and then it jumps to the reset entry point at 2080. Now, reset sets the counter byte to 0 and it stores the byte at 2500H. So, from reset, we fall into the show subroutine. It calls the command at 0F4D and it clears the kit LCD. It loads the counter value from the 2500 that we stored it at and it runs the decimal split loop and it displays both digits using the two calls. After displaying, we enter the poll loop, which is basically uh, 10 iterations, 100 millisecond delay. So we are polling at 100 milliseconds to make sure that if a key is pressed, we can register it. On each iteration, we read the keypad rows and read the columns, and we compare them against the 0 to H, like I explained earlier. And if the key 1 is held, we jump straight back to reset. If not, we delay and then we decrement the loop counter. This is the delay subroutine. This is the reset subroutine. And this is the initialization startup code. That is basically the whole program that we have. Now let's look on to a more interesting part of the code. When I started implementing the timer, it was displaying addresses or the time in hexadecimal, but that's not what we want, so we need to convert it into decimal. So the 8085 doesn't actually have a divide instruction, so we cannot just divide it by 10 to get the tens digit. So we use an algorithm that is based on repeated subtraction. The algorithm, as you can see on the left, we load the counter from 2500H, which has the stored timer value. We save a copy of it in the register E, and we set the register D to 0. The register D will accumulate the tens digit. We enter the sub 10 loop, and we compare A against 10 decimal. If A is already less than 10, then we're simply done. But if not, we subtract 10 from it and then increment D and then loop back. Finally, when we exit the loop, the D holds the 10 digit and the A holds the units digit. So we move A to C to save it and then load D into A and add 30H to convert the digit into 0 to 9 characters of the decimal digits. We basically want to convert it into ASCII characters instead of just like normal decimals. And then we call the LCD command to display it actually on the LCD. If we look at the trace on the right side for a counter value of 47, we start with that is 47 and D is 0. In the first iteration, 47 is greater than 10, so we subtract 10 from it, A becomes 37, D becomes 1. We keep on going to this loop until A becomes 7 and D becomes 4. And we can see that we have the units digit and the tens digit separately. We convert it into ASCII and display it straight away on the LCD. This algorithm runs in at most 9 iterations for values from 0 to 99. Now let's look at the timer loop code. On the left, we have the reset and the show section. The reset starts at 2080 and it takes three instructions. First, we load 0 into the accumulator, then we store it at 2500. The show subroutine starts at 2085 and its first call is to clear the kit LCD and it returns the cursor to home so that we can start writing from there. and then we load the counter from 2500. We copy it to the register E, set D to 0, and enter the loop just like I explained. Again, just like I explained, the loop compares against 10. If it is greater than, it subtracts until it's not, and that's where that it calculates decimals. And then we end it with displaying it on the LCD after converting it into the ASCII character. On the right side, we can see the polling section of the code. So basically, we poll the keyboard values again and again, and we do 10 polls per second to make sure we do not miss any key presses. And it loops and then it writes at 07H to port 0A, which is the 8255 port C, 8255 2 port C, and it makes sure that whenever the key 1 is pressed, it jumps to the reset subroutine and it resets the counter. If not, we just kind of loop back and keep polling. When the loop finishes, we load the counter value from 2500, we increment it, and then we compare it. And like I said, we get the decimal value from it. And then we jump to the show subroutine, which displays the value. Okay, so if we look at the displaying code, the LCD code, so the LCD subroutines are at fixed addresses, like I said earlier. The WRCMD, which is at 2048, it takes a command byte and register A. The first instruction out 00H, as we can see on the left side, it puts the accumulator value into the port A of 82551, which is connected to the LCD. And then we load the data 04H into A, and then we write it into port C. So now the LCD is seeing a command on the data bus which has enable as high. And then we write 00 to port C, E falls back down to 0, and the controller latches to the data. We call the delay to subroutine, and then we return back. The WR subroutine at 2056, it is almost identical, except that we use 05H and 01H for the port C values, which means that we are indicating a character data rather than a command. There are two delay subroutines at 2064 and 2006B addresses. The delay 1 subroutine, it counts C down, and the delay 2 subroutine, it counts from FFH. It it has a difference in the length, which is why the WRCMT, it uses delay 2, and the WRCHAR, it uses delay 1. So commands like clear display trigger only internal LCD operations that take longer than a simple character write. So let me just quickly quantify the timing to show how we arrive at approximately 1 tick per second. So the KITS 8085 runs at approximately 3 megahertz. So which is basically approximately one cycle of 300 nanoseconds. And then the delay subroutine, it follows the manual, and its total time equals 24 times DE plus 17, which is measured in T states. So we load DE with 20FFH data, which is 8447 in decimal. And if we plug it in and multiply and do the calculations, we approximately arrive at 65 milliseconds per pole. If we poll 10 times, so the window for polling is approximately 650 milliseconds. And on top of that, each display cycle, it also calls a clear LCD routine, which involves delay 1 and delay 2 calls. This approximately adds 25 milliseconds. So the total time is approximately 680 milliseconds. But this is not exactly 1 second, but for a visual demo, it is almost the same. So for a timer like this, it works quite well. Now, if I move on to the key challenges that I faced while making this and the solutions to the challenges. So the first problem was that there was a call which was the command call 1133, and it had a problem with the monitor hex display. It was corrupting the register B. The initial design was to store the counter in register B, but we used to get a different value every time we pulled that register. So I decided to instead store the value at 2500H in the RAM instead of trying to store it in the register B, and it worked quite well. The second problem was that the LCD was showing the counter in binary, like it started with 00, then 01, and then 10. But that's not exactly what we want. We want it to be used by humans, so we would want it to be in decimals. So we had to add a decimal loop, which made sure that that binary was being decoded into decimal, and then we make that into ASCII, and then we display that on the LCD. The third problem was with the 82552 port, since I was trying to get the external LCD module on the 82551 and the keypad on the 82552. Usually, all of the code examples given in the lab manuals were not really given for the 82552 port, so it was a problem trying to figure it out. But finally, we kind of verified that using the original like 8085 lab kit guide, and in there was one example using the 82552 port. So from there we could know the addresses of the port and how to call it. And fourth is kind of one of the main failures, that the LCD module was not working reliably. Although the LCD module was only meant to display a static message, but I also tried to use that, but for some reason the hardware wasn't working. But again, like I said, that wasn't the main part of the video. The main part was to show a timer on the built-in LCD display, not the external one. So a timer on the built-in display which counted up in decimals and which could be reset using the keypad. And I successfully managed to do that. And finally, the fifth problem was that the startup code was kind of overflowing into the subroutine space at 2048. And since that is needed for the LCD initialization, um, there we had to put a jump keyword at the 2000 address, so that we can just straight jump to the routine and put the routine at an entirely different memory location. But that was also easily solvable, and it was not hard to debug. Now I will show you the live demo of the video. I will play the video clip, and you can see how it actually worked in practice. So this is my project for the innovation part of this course. So if I run this program, it starts a timer which counts up in decimals. It starts from 00 and goes up to 99. I here have connected a keyboard module to the J2 port and an LCD module to the J1 port. As you can see, if we press the 1 key on the keypad, the timer starts back again from 0. I'll show that again. So it is basically a keypad controlled decimal timer which counts up from 00 to 99. And the way that this code works is that it converts the binary hexadecimal values to decimal values, which shows the timer in decimals. And also it polls this keyboard 10 times per second to make sure that whenever the key is pressed, we register the input and the timer starts back again from 00. I also tried to incorporate this LCD module, but for some reason the module isn't working. But as you can see, this is my innovation part for the video. Alright, after seeing the demo, you can see how we practically executed that. and I will show you a compiled list of the results that we got. So the keypad matrix scanning, it worked and it was verified. I actually even used an oscilloscope, and I wrote a small test program which would check which would make the voltage high if the keypad was pressed and low if it was not. So I could test if the keypad worked on the 82552 port or the J2 port using that. But again, like it worked, and then I finally integrated it with the counter and also the decimal counter display. As you saw, it was working correctly. Uh, it started from 00 and it would go all the way up to 99, after which it would reset. Or you could press the number key on the keypad and it would reset immediately. And finally, all of the memory layout and the subroutines were correct. We had the WRCMD command at the correct position, the WRCHAR command at the correct position, and the timer loop at the correct position. And using the jump at 2000H, we successfully routed the program around the subroutine space. Now, let's look at the applications for this as they are necessary for any kind of project. So, uh, the techniques that we demonstrated in this practical, they can have applications into real embedded systems. The most immediate extension for this is a real-time clock. I mean, right now we count from 0 to 99 seconds, but we can extend this by adding hours, minutes, and seconds counters. And we can add a minutes counter that increments when seconds hit 60, the counter that increments when the minutes hit 60, and so on. We could even replace the counter with an ADC reading, and that will give you a decimal sensor display basically. If we attach a temperature sensor to the ADC unit on the kit and we scale the raw byte data to degrees, we can display the result in decimals. So basically, we can get a temperature reading. If we use the same keypad scanning code with a slight modification, it can also give you a pin entry. If we map the individual keys to individual digits, you can actually enter a pin using that. If we use a frequency counter and we connect an external signal to a keypad port bit, and we use the 8253 hardware timer to define a 1 second window, then we can display the count in decimals, and it gives you a basic frequency counter without any kind of external dedicated hardware. And of course, the countdown timer extension is quite simple. You start from a user entered value, and instead of counting up, you can count down, and you can have uh, it display when the timer is finished and it hits 0, which is basically kind of like a stopwatch. Now, finally, after this long presentation, I want to take a step back and like give an overview of what we learned. So the fundamentals of this peripheral interfacing, as we see, they are the same. The 8255 PPI, it has been introduced for a long time. And even in like 2026, we are still kind of using that or learning from that, because it helps you understand that if you can configure a port direction and you can write to its outputs, you can read from its inputs. If you understand this, then you can understand really how most electronic devices work. Most devices that use microprocessors or microcontrollers, you can really understand how they work. The second thing is that software can kind of replace hardware, because we did not really have any kind of binary to decimal converting chip, but we wrote a program within a kind of self-complete 8085 processor. So we didn't really need any kind of specific hardware. We just needed a cleverly written software code in a general microprocessor which can run that instead of needing any kind of separate hardware. The third kind of benefit of this is that memory layout is actually a design constraint. It is not just an exercise. It actually happens in real life if you write low level code or assembly level code. So we need to be able to think about that and work according to that. And finally, we know that debugging is methodical. I mean, you can't just expect to kind of type in the code and everything just runs smoothly. I mean, there will be errors and you would have to debug that. And it takes patience and it takes a good understanding of how things work. We also learned that from this experiment. So, to summarize, we successfully implemented a keypad matrix which was scanning on 82552 port, and we saw that if the decimal display works correctly and you convert the decimal to the ASCII code also correctly, the display was clean and stable. The final program was approximately 200 bytes of handwritten 8085 machine code, and it demonstrated input-output port configuration, peripheral interfacing, software timing, decimal arithmetic, and memory layout planning, and even debugging, how to debug code. So, thank you. That is my presentation, and I hope you guys enjoyed it, and I hope that this inspired you to do projects on your own.